Assalamualaikum to my lecturer and to all my friends. We are from Group 5 and today we will explain about our engineering drawing project. Our topic project is production of syngas from municipal solid waste in Pakistan. Before that, I will introduce myself. My name is Nur Fatina Diha binti Alizul and my another groupmate is Nur Hanisa binti Zulkifli, Zida Kamalia binti Abdul Wahid, and I'm Syahira Izzati binti Nur Izzat. First of all, I will explain about our background of development production. The development of the syngas production system from municipal solid waste using a circulating fluidized bed gasifier was driven by the need for clean energy and sustainable energy sources, especially in regions with high municipal solid waste production rates and limited resources like Pakistan. The system aimed to address environmental concerns related to waste management, such as reducing the amount of waste sent to landfills, minimizing the environmental impact of waste disposal, and reducing greenhouse gas emissions. By converting municipal solid waste into syngas for energy regeneration, the system aims to enhance energy security and reduce dependency on traditional fossil fuels for power generation. The integration of a circulating fluidized bed gasifier with a carbon capture process in the syngas production system demonstrates a commitment to utilizing advanced technologies for efficient energy conversion and environmental protection. Research focuses on evaluating the energy conversion performed of the integrated gasification process through material and energy balances, highlighting the potential benefits of utilizing municipal solid waste for energy regeneration. The potential of municipal solid waste as a valuable resource for energy production through gasification, highlighting the importance of sustainable waste management practices and resource recovery from municipal solid waste. The capacity of the syngas production plant is determined based on the availability of feedstock, which in this case is municipal solid waste. Municipal solid waste gasification is seen as an effective process that not only help in solving the solid waste problem but also reduce the need for waste disposal in landfills. Municipal solid waste is described as a heterogeneous resource containing various materials such as paper, food waste, wood, cotton, leather, and fabrics. Proper segregation of municipal solid waste into waste categories can enhance the homogeneity of waste streams, optimize waste reuse and recycling, and maximize the benefits of treatment alternative for each category.
So, we move to the next part, which is block flow diagram. I will explain to you all about block flow diagram that we create. We use municipal solid waste as a feedstock. Municipal solid waste consisting of everyday household and commercial waste is the primary feedstock for the gasification process. This waste undergoes a conversion process to produce a synthesis gas, a valuable intermediate for producing various chemicals and fuels. Next, we move to the air separation unit, which is cryogenic. Input is air and output is oxygen and nitrogen. This unit separates air into its components, primary oxygen and nitrogen, using cryogenic distillation. Pure oxygen is crucial for the gasification process as it ensures the syngas produced is free from atmospheric nitrogen, enhancing its quality. Next is gasifier. Input is municipal solid waste and oxygen. The output is syngas, which is 800 degrees Celsius, and ash. In the gasifier, municipal solid waste is converted into the synthesis gas at high temperature, which is 800 degrees Celsius and atmospheric pressure. Oxygen from the air separation unit is used to facilitate this conversion, resulting in a mixture of carbon monoxide, hydrogen, and other gases, while ash is left as a byproduct. The next part is syngas cooler 1. Input is syngas, which is in 800 degrees Celsius, and the output is cooled syngas. This cooler reduces the temperature of the synthesis gas from 800 degrees Celsius, making it suitable for further processing. Cooling the syngas is essential for the subsequent impurity and the reaction optimization. Next, we move to the scrubber, which is H2S removal. The input is cool syngas and sodium carbonate. The output is clean syngas and S-rich steam. The scrubber removes hydrogen sulfate and other impurities from the synthesis gas using sodium carbonate. This purification step ensures the syngas is clean, preventing sulfur-related issue in downstream process.
Next, after the purification process is done inside the scrubber, then the syngas is finally free from hydrogen sulfide and it produces a clean syngas, right? Okay, so this clean syngas will go to the next process, which is methanation process. But before that, it will be divided into two parts, where the first part is that the 35% of clean syngas will go directly to a compressor, whereas the remaining, the balance, which is 65% of clean syngas, will have to go through a carbon monoxide shift reactor first, and then only can go to the compressor. So what does this carbon monoxide shift reactor do? So inside the reactor, there will be a reaction called water gas shift reaction. That is a reaction with the presence of steam. So in this reaction, steam reacts with a carbon monoxide contained in syngas, producing a carbon dioxide and hydrogen. And the purpose of this reaction is to enrich the hydrogen content inside in the clean syngas to make it more suitable for further process, which is the methanation process. Okay. And then we move to the next unit, which is compressor. So the clean syngas that is directly from the scrubber, the 35% and the 65% clean syngas that have been enriched the hydrogen content will then go to a compressor, and inside this compressor the clean syngas will be highly pressurized to 28 bar. 28 bar is a standard range for a biomass, but the range is in between 20 to 30 bar. But in this case, we use 28 bar because it used biomass. And then, this high pressure is necessary for methanation process because it's facilitating the conversion of hydrogen and carbon dioxide to methane. And then, after that, so the output is the compressed syngas, right? Okay, then this compressed syngas is then moved to the methanation unit. So in this methanation unit, we convert the compressed syngas into methane and ethylene. So the compressed synthetic gas will undergo a catalytic methanation, converting carbon monoxide and hydrogen into methane and ethylene. Then inside this process, it operates at high temperature, which is 350 degrees Celsius, and also it uses a nickel-based catalyst. Next process is Salicyl process. So what is Salicyl process? Salicyl process remove carbon dioxide from gas mixture using a solvent, monoethanolamine, and water solution to absorb the carbon dioxide. So this process remove carbon dioxide content from the final product of the methanation process by absorbing the carbon dioxide using a solvent, where the solvent are monoethanolamine and water solution. Okay, So the process results in a high purity of remaining gases, which is methane and ethylene, making the final product stream is ready for use and for further processing. So the main purpose of this dialysis process is to remove carbon dioxide content from the methane and ethylene by absorbing it. Then next process will be explained by Hanisa.
We add some additional information about our block flow diagram. First of all, why is sodium carbonate present in the input of the scrubber? Sodium carbonate is used in the scrubber for the removal of acidic gases, particularly hydrogen sulfate from the syngas. Sodium carbonate react with hydrogen sulfate to form sodium hydrogen sulfate and sodium bicarbonate. The scrubber with sodium carbonate not only remove hydrogen sulfate but can also help in the removal of other acidic components like carbon dioxide and sulfur dioxide to some extent. To its primary role in this context is hydrogen sulfate removal. The second one is why carbon dioxide is removed in the Salesol process. Carbon dioxide is removed from the syngas in the Salesol process to purify the final product, gases mainly methane and ethylene, and to meet quality requirement for their intended use. For methane and ethylene is to be used as fuels and chemical feedstock, they need to be of high purity. Carbon dioxide is considered an impurity that can affect the quality and performance of these gases in their application. In subsequent processes that use methane and ethylene, catalysts are often used, and the presence of carbon dioxide can negatively affect these catalysts, reducing their efficiency. Removing carbon dioxide from the product stream can help the reduce greenhouse gas emission if the carbon dioxide is captured and sequestered or utilized in other industrial process rather than being released into the atmosphere. The third part is why does the output scrubber have S-rich steam? The term S-rich steam refers to steam that has absorbed sulfur compounds, particularly hydrogen sulfate, during the scrubbing process. The cool syngas containing hydrogen sulfate and other impurities enter the scrubber. In the scrubber, the syngas is treated with a scrubbing agent, in this case sodium carbonate. The hydrogen sulfate react with sodium carbonate to form sodium hydrogen sulfate and carbon dioxide. The chemical reaction stated in the slide, as you can see, and the steam is often injected into the scrubber to aid in the absorption of sulfur compound. The steam helps maintain the required temperature and pressure for the reaction and enhance the mass transfer of hydrogen sulfate from the gas phase into the liquid phase, where the scrubbing reaction occurs. As the scrubbing process proceeds, the steam absorbs sulfur compound primarily to form sodium hydrogen sulfate. This results in steam that is rich of sulfur compound, hence the term of S-rich steam. So, that's all of my part.
We move to the process flow diagram, PFD. First is air separation unit, cryogenic. 8.2464 kg per second air enter the air separation unit, where it is cooled to cryogenic temperature to separate 6.3497 kg per second nitrogen and 1.8967 kg per second oxygen. It moves to the gasifier. 5.154 kg per second municipal solid waste and oxygen enter the gasifier. which are operating at 900 degrees Celsius at 1 atm. The gasification process converts municipal solid waste into syngas with ash as a byproduct. Then it moves to the syngas color 1. The hot syngas from the gasifier is cooled down in this unit. Then it moves to the scrubber, which is H2S removal. The syngas enter the scrubber with sodium carbonate is used to remove the hydrogen sulfide from the gas. The scrubber produces a sulfur-rich stream and clean the syngas. Then it goes to the CO shift reactor. The clean syngas undergoes the water-gas shift reaction in the CO shift reactor. This reactor increases the hydrogen content of the syngas. Steam will also add, and 65% of the clean syngas continue through the process. Then it moves to the compressor. The remaining 35% of the clean syngas is compressed to 28 bar over the processing. In a cooler 2, the compressed syngas is cooled down to 250 degrees in this cooler. Then it moves to the methanation unit process. At 350 degrees Celsius, the syngas undergoes methanation, which produces 0.497 kg per second of methane and 0.114 kg per second ethylene. The process is also produce the carbon dioxide. Then it goes to Cell-Extrusion process. Cell-Extrusion process involves an absorption unit, stripping unit, and lean-rich stream. This process is used for the selective removal of CO2 from the syngas and also for the purifying for the final product use.
So lastly, the conclusion that we got from this production is the production of syngas from municipal solid waste through gasification represent a promising approach to address both energy and waste management challenges, offering a sustainable and environmentally friendly solution for energy generation and resource recovery. The gasification process for municipal solid waste has the potential to regenerate energy efficiently with significant total energy potential of 30 MW based on a reference plant capacity of 50 MW. Careful design and evaluation of material and energy balances for individual components of the gasification system are essential for optimizing energy production and system performance. Municipal solid waste gasification not only contributes to energy production but also helps in solving solid waste issue and reducing the reliance on landfill for waste disposal. Gasification of municipal solid waste into syngas provides a clean energy alternative, particularly in regions with high municipal solid waste production rates and limited resource like Pakistan. I think this production should be maintained because it will achieving a sustainable energy future, promoting efficient waste management practices and realizing environmental, economic and social benefits associated with renewable energy production from waste resources. There are a lot of ways to maintain this production. For example, involving local community and key stakeholders such as environmental departments to raise awareness of the benefits of municipal solid waste gasification for energy production can help garner support for such initiative. Next, building partnership with relevant organizations and involving the community in waste management efforts can contribute to the success and sustainability of the syngas production from municipal solid waste. Proper management of municipal solid waste feedstock is crucial to ensure a consistent and reliable source of material for gasification. Implementing effective waste segregation practices and ensuring a steady supply of suitable feedstock feedstock can enhance the overall performance of the gasification system. So I think if the government in Malaysia do the same thing like Pakistan, we also can reduce our solid waste in landfill, and also it can save our environment in Malaysia. That's all from us, and thank you to my lecturer and my friends. Assalamualaikum.